All right, welcome to part 5 of our Unit 1 Scientific Foundations of Psychology. Today we're going to be looking at understanding data and statistics and kind of delving into this a little bit. All right, so what we're going to talk about first are what are called descriptive statistics. Now this is most of what we were going to be looking at and most of what you'll probably be using when you talk about data and statistics. There is a separate type which is called inferential statistics. We'll talk about both towards the end of class, but just knowing that there's two, right? So what are descriptive statistics? Really simply, that it's pretty much all in the name, right, is that these are statistics that describe a set of data, okay? So you've got a whole bunch of numbers, got a whole bunch of data. These are ways that we can describe them. And all of the stuff that has to do with descriptive statistics are describing that data, okay? So a really simple example is something like a frequency distribution, right? And we're going to see those, a whole bunch of different versions of those today, right? So basically, it's a list, a table, a graph, right? Anything that displays the frequency of various outcomes in an example, okay? Now, there's a lot of ways to look at it. I've got 3 different ways on this slide right here. The first way is down here at the bottom. So if you look straight down on the right, so you're going to basically say, I want to know the number of pets that people have in my class, right? So we went out and we basically surveyed everybody and we collected a bunch of data, right? One way to represent that data, to see the distribution, is through this table, right? So we've got the number of pets on one side, 0, 1, 2, 3, or 4, right? We've got our tallies, which is our raw data down the middle, and we have our frequency. Right? Now notice our frequency is the exact same as the tallies. It's just how often are we getting that answer. So, 4 students had no pets, 6 had 1, 5 had 2, 3 had 3, and 2 had 4. Right? That's just our data. Okay? And then now it's just been put into this idea of frequency. Now, 2 other ways that we can show this information, right, that we can describe this data that we collected, is through a frequency polygon or a histogram. Okay, so frequency polygons are just a line graph of frequency distribution. Okay, so on the bottom left here, right, you'll see basically this graph. That line part, right, that's going from one to another, is the frequency polygon. Okay, all it is this data right here turned into a line graph. Okay, a histogram is the same thing, except for it's in that bar graph form. Right, so we're just seeing those bars. Right, again, they're representing this exact same information, the exact same thing that our line graph is showing. It's just a different form. Right, now I just put both of them on top of each other. Now, one thing to note, right, is that generally speaking, you're not going to see like a true line graph like this, right, a true frequency polygon where it's like these straight lines from one to another. You're generally going to see a smooth curved line. Okay, now the reason for that is that statistically speaking, right, we also want to be able to calculate this for any number, right? We don't want it to just be the one information that we have. So when we smooth it out, basically what it allows us to do is decide, okay, anywhere on this line, right, we can find an exact answer, okay? Anywhere on this line. So again, we're often going to see it as kind of a smooth curve. So for example, right here, right? So when we look at these distributions, there's certain things that we want to learn from them. Right, and actually if we go back, we can also look at this as well, right? We can see what kind of curve this is going to be by applying it here, okay? So there's 3 basic types of distributions or ways that we read distribution. Let me move myself out of the way again here. So the first one is what is called a normal distribution. Okay, a normal distribution is just one that is perfectly symmetrical, okay? So it's right here in the middle. This is what we call a normal distribution. You also may have heard it called like a bell curve or a normal curve, right? All of those things mean the same thing, okay? Now the idea is it's exactly symmetrical, so I could fold it in half and it would be the exact same, okay? Now notice again, right, our frequency, right, is always going to be that y-axis. Our whatever else we're looking at is going to be that x-axis. So our highest point, right, is going to be exactly in the middle of a normal curve. That's how it always folds. Okay, because again, it's the same on each side. Then we also have a negatively skewed curve and a positively skewed curve. Now again, these are basically this same kind of idea, just flipped, right? So what we're going to see is that a negatively skewed curve is where we have a few small outliers, right, low scores, right, that are considered outliers that pull that graph, right, towards the outliers. Okay? The skew is always going to be pulled towards the outliers. So we've got a few really small numbers, and what it does is it pulls that curve over, it kind of gives it that tail. That's that negatively skewed. Okay? To be really clear, just because it's negatively skewed does not mean it's negative numbers. It just means it's skewed towards the smaller numbers. Okay? Positively skewed curves are basically the exact same thing, right? Just towards the positive. So if we have a few really high numbers, right, a few really high data points, it's going to pull that curve towards those data points. Okay? Now a simple example to kind of think about this could be something like height, right? If we wanted to find, the frequency of different heights, right? How often is someone a certain height, right? We could line everybody up, right? And we could create, we could find this frequency curve. I'm just going to go back. We could find this data, right? We could make a histogram, right, of all this data of everyone's height. And then we could basically place it on these curves, right? Now, generally speaking, what we would expect is to find a normal curve when it comes to height, right? Because most people are going to be average height, right? That's why it's called average height. Most everyone is going to be pretty close to a certain rank, right? Now, there's probably, as we go and get shorter and shorter, there's going to be less and less people, right? We're going to find that there's less and less people that are under, let's say 4 feet tall, right? There's some, but it's going to be a very small number, right? We find the exact same thing on the other side, right? If we're getting toward taller and taller and taller, right? There's some people who are really tall, 6'7", 6'8", 6'9", right? People that are 7 feet tall, right? But it's going to be a very small number, of people that are 7 feet tall. Okay? So that's where we would see this normal curve here. Now, if we wanted to do the same thing, but let's say now we were only looking at our classroom, right? Let's say we were looking at our class. Well, when we look at our class, right, what happens if there's one person in our class who's 6'10", right? Well, the reality is that one person is going to pull all of our data way over, right? Because of their being so tall, right? We can see the same thing happening, right? On the other side, if we had someone who was maybe 3 feet tall, right, they would pull our data towards that lower frequency, okay? So again, we're just kind of seeing how that shifts things around a little bit. Now, another way that we can describe data, right, is through what are called measures of central tendency. Okay? Now what these are basically a single score number, right, that's going to represent the whole set of numbers. Right? Now again, the idea is I've got a whole bunch of data, a whole bunch of numbers, but I need to be able to effectively give that to somebody else and have it mean something. Right? So if you guys ask me hey, how did we all do in the last test? Right? Not how did I do as an individual, but how did our class do? Right? If I just started listing every single person's score, that's not super helpful necessarily, right? What I would probably give you is something like the average, right? So, and that average number tells you about the whole class, right? Just with that one score. And that's the idea of measures of central tendency. So there's 3 kinds. I'm sure you've heard them all. I'm sure you know how to calculate them all, right? We have mean, median, and mode, right? Mean is the average. So to find it, we sum up all of the scores, right, and then divide it by the total number of scores. Our median is the midpoint, so it's exactly halfway in our data. It's always going to be, it also can be called what's called the 50th percentile, right? So percentiles are going to always start 10%, the 10th percentile is going to be the smallest, right, or really low, and on. 50 is going to be perfectly in the middle. 90th percentile would be really high, okay? Then we have our mode. Our mode is just going to be the most frequently occurring score. So our mode is always going to be the top of our chart, the highest frequency, okay? Now, one thing that's important to notice is how these numbers, how these measures of central tendency are related to these different skews, right? Because if our graph is skewed, it also affects our mean, median, and mode, okay? So in a normal curve, right, our mean, median, and mode are the exact same number, right? They're all going to fall right perfectly in the middle. Now, when we have a skewed curve, what's going to happen is that's going to pull the mean and the median. The mode is never going to move. The mode is always going to be the top of the curve no matter what, okay? But our mean and our median are going to be moved by that skew, right? Now mean is going to be moved the most because it's going to mess with the average the most, right? If we have a really, really tiny number, it's going to mess with the average more. It's going to pull the average a lot. If we have a really, really high number, it's going to do the same thing. It's going to pull the average, okay? Now median will also be affected because those outliers will have a little bit of effect, but it won't be as big, okay? Now this is important because one, they'll ask you questions that are very specifically like that. They'll give you like a whole bunch of, maybe like a list of data, like 6 numbers or something, and they'll say, if we add this number, how does that affect the mean? Right? Now, generally speaking, you don't have to do the actual math, but if you notice that number is really, really high, well, then you know, okay, it's going to shift the mean positively, right? It's going to move it way to the right. If it's really low, you're going to know, okay, it's going to move it really far to the left, okay? But it's also really important when we know about, like, how we're going to talk about something. I think most of the time we like to think that mean is the best form of central tendency, but it's not necessarily true. Right? A really simple example is like if you go right now and you look up like jobs, like you look up different types of jobs that you might want in the future, a lot of times what you'll find is that they'll give you, like if you want to look at the salary, they'll give you the salary based on the median, right? Now the reason for that is really important. It's because generally speaking, job payment has a curve like this, right? There's a lot of people at the beginning, right? And then there's that are making, you know, about the same amount of money. And then there's a very few amount of people who have maybe been doing it for a really long time or a really, really high level that are making a ton of money, right? And the reason that's important is if they would have given you the mean, it would seem like you're going to make way more money than you actually do, right? A simple example is something like as a teacher, right? There are teachers that make $100,000 some dollars a year, right? More than that even sometimes. But it's a very, very small number, right? Where most of us, right, are going to sit closer to like, I don't know, 30 or 40,000 depending on where you live, right? So if they would have said, oh, here's the mean pay, well, I'd be like, oh, I should be making way more money than I actually do, right? So if they give me the median, that's more realistic. It still accounts for it a little bit, but it's closer to what's likely to happen. Now that gets us to what are called measures of variability. So measures of variability are going to oftentimes be used with a measure of central tendency. Right? Now again, remember, all this stuff is just about describing data, describing the numbers that we have. Okay? So for measures of variability, right, what this is going to tell us is how similar or diverse scores are. Right? Basically, how variable is the data. Right? How spread out or close together are the numbers. Okay? Now a lot of times what it's going to tell us, if you look at this graph here, is basically what the graph looks like. Right? Measures of central tendency kind of tell us maybe it's skewed or not. It tells us kind of where that center point is. But a measure of variability is going to tell us like how tall or thin or short and kind of wide those different charts are. Okay? Now there's 3 different ways to look at variability. There's range, variance, and standard deviation. Okay? Range is our first one. Range is going to literally just represent the range of the data, the span of the scores that we have. Now, range is probably like our least useful, and we'll see that in kind of what we do. All you need to do to find the range is take the biggest number and subtract it from the lowest number. Okay? So, I'm sorry, the lowest number and subtract it from the biggest number. So, our high in this set of data right here, right? Our biggest number is 283, that's our highest score. Our lowest score is 12, so 283 minus 12 is going to be a range of 271. Okay, now again, not super descriptive, which is why we don't really use it too often, but it does tell us, you know, how far apart the biggest and the lowest scores are. Now, a better way that we can kind of talk about variability or variation is variance. Okay, so what variance is going to do is variance is going to give the distance between the numbers and each other and the mean. All right. So how far apart they are from one another and from the mean. Okay? So it's basically talking about how spread are the scores. Okay? Now the thing about variance is it's looking at each individual score basically. Okay? So every single point of data, it's going to say it's this far away from each other in the mean. Okay? Now, I put kind of how to figure these out. Generally speaking, you don't have to do any like real math on the AP Psych test. But I found that it can be a lot easier to understand what they're asking if I can do the math, right? And then kind of the idea is that you don't need to do the math, but you'll know, okay, if I add this number or I take away this number, how would that affect it? You know what I mean? You're not going to have to find the real number, but you can say, oh, it's going to get smaller or it's going to get bigger. Okay? So there's 3 steps to finding variance, right? The first thing is you need to find the mean of your numbers, right? So let's pretend our numbers are 1, 2, and 3. Okay? So if I add those all together and divide them by 3, right? It's 6 divided by 3. My mean is 2. Okay? So once I have my mean, right, what I need to do for each number is I have to subtract the mean and the square, and then square the result. Okay? So I subtract the mean, so for each number, 1 and 2 and 3, right? I have to subtract the mean, which is 2, so minus 2, minus 2, minus 2. And then I need to square the result, so square. Okay? So I do all that math. Then I have to find the average of those differences, right? So the way I just do that is I just, again, to find an average, I divide it by the total, right? So I add those numbers together, and then I divide it by the total numbers, which is 3, and then what's going to spit out is the variance. So for this set of numbers, the variance is 0.667. Okay? Now again, what this is used to do is describe how far away these numbers are from each other and from the mean, right? And that's why it's not 1, because you might say like, oh, they're all 1 apart, but it's from each other and the mean, right? So that's where it's going to be a little bit different. Okay, but again, the idea is if I've got a really small, and this is standard deviation as showing, but a really small variance would look like this. It'd be tall and skinny, right? And a large variance is going to look like this, right? It's going to be shorter and wider. So that gets us to standard deviation. Now, standard deviation is what we use the most. One thing that's kind of important is the numbers that we actually use in standard deviation, these percentages, are always going to be the same, okay? And you actually need to know them. This is something that you want to draw or literally write these numbers down, because they do expect you to know when they say 1 standard deviation, they expect you to know what percentage that means, okay? So, what is standard deviation, right? Basically, it's the average distance from the mean for a set of numbers, okay? Now again, it's a set of numbers. So it's kind of similar to variance, but it's breaking it into groups, and you can see that, right? We've got 1 standard deviation is these green parts, 2 standard deviations is this yellow, 3 is the red, right? And on. You can see that here as well, right? So it's basically splitting these groups in together. And so what it would say is for this group, right, it's this far away from the mean, the average. For this group, the average is this far away from the mean. From this group, the average is this far away from the mean, right? Again, it's kind of doing the same thing, but it's just chunking it into groups. Now, to find the standard deviation, right, all you're going to do is do exactly what we just did for variance, right? So all these steps, and then you're going to do the square root. So we take the variance and we square root the variance, okay? And the idea is, again, we're trying to figure out how variable is our data. So how tightly packed are our scores? Are they spread out or are they close together? Okay. Now, I guess a few things maybe before I even go on, I'll give you kind of a little break. One thing to know, I do have a worksheet. I think I'm going to give it to you guys next class, or when you guys have this class for this. And it'll basically walk you through the math of doing standard deviation. Okay. Now again, they're not going to ask you to do it, but if you know kind of the process, when they ask you, okay, if you add this number or if you take away this number, what's going to happen? You'll be able to kind of better get an idea of, okay, this is how it'll change. Okay, so again, you don't have to memorize these math problems or anything, but you just want to have a general idea of how they work. Okay? Now, standard deviations always look the same. Okay? Now, we do standard deviation on a normal curve, right? It always is going to break down the exact same way. Okay? 1 standard deviation, right, which is this first section here, is always going to be 34.1% above average and below average, right? Above and below that average number in the middle. Okay? So when we talk about if you're within 1 standard deviation, right, that's 68.2%. Whoops, I'm sorry. That's a video that's going to open up. It's 68.2%. Okay? And again, I would literally just draw this exact same graph here. If you're within 2 standard deviations, right, it's an extra 13.6% on each side. Okay, now everything within 2 standard deviations is all this. That means we're accounting for 95.4% of all the answers, right? All of our scores. 3 standard deviations, right? We're adding 2.1 on each side is going to account for 99.7% of all of our scores. Okay. Now again, what we would find here is kind of the bigger number, right? That we're finding, the bigger standard deviation that we have is going to mean that these percentages get, like their percentages are always the same, but the number range is going to get bigger, if that makes sense. So if my graph is really short and wide, it's going to have a bigger number, even though the percentages are the same, right? Because those percentages would get wider, kind of like here. If it's really compact and tall, right, it's still going to be this exact same percentage, but it's going to be a much tighter, narrower group of numbers. Okay. Now, and when we talk about this, we'll go through basically the standard deviation and this idea when we talk about intelligence, because this is exactly how intelligence scores fall. Okay, and the idea is, again, we can kind of explain and describe these different ideas within here. So within 1 standard deviation is considered like average intelligence, right here, and that is 68.2% of people. Right? Now, if you're within 2 standard deviations, if you're 2 standard deviations on the positive side, that would mean you're above average intelligence, right? If you're on the other side, you're below average intelligence, right? If you're 3 standard deviations out, right, on the positive side, you are like a genius, right? You are more intelligent than basically 99% of the rest of society, right? If you're on the other side of that, right, it means you're like less intelligent than 90% of intelligence, right? That's people who have cognitive disabilities, right? Severe cognitive disabilities, right? And we can kind of continue on. So again, it's a way of kind of breaking up our data to better get an idea of it. And we'll talk a lot about standard deviation. There's also 2 videos, which is one I accidentally clicked on. They should both be in Canvas already. I really suggest watching those. One of them is like from the Crash Course Statistics, AP Statistics, which is they talk about stuff that's a little different than what we do, but it'll give you a pretty good idea, and they'll kind of explain what we're talking about. There's 2 videos there to help you with standard deviation. So our last piece here is what are called inferential statistics. Okay, so we talked about descriptive statistics and how the whole idea of them is to describe our data, describe our numbers. Inferential statistics are going to do something a little bit different, right? Instead of describing the data, they want to know, can we apply this data to the larger population, right? Whether or not we can apply what we found to this bigger group, okay? Now, this is really, really important because if our data isn't applicable, then it doesn't matter, right? It doesn't do anything. We can have all sorts of data, but if it doesn't apply to the bigger group, well, then it doesn't tell us anything, okay? So ways that are like types of inferential statistics are using things like t-test, chi-square test, and ANOVAs. Now, you guys do not need to know what those are. You do not need to ever be able to do them. You might have to do them in like AP Stats, but I don't care about them, so don't worry about them, right? All you need to know is all those tests are going to spit out what is called a p-value. Okay, the p-value is what's important to us. We're going to talk about it in 1 second. Again, I just kind of want to point this image on here because it gives us kind of a good example, is when we do any type of study, right, we've got a giant population, we take a sample, right, so we pick a group of people, we pull them out, and then we do whatever we're going to do, we do our study, right? We take all that data that we get from our study and we create our descriptive statistics, right, like it says down there. So we have this finding that, 90% of people like pizza, right, whatever. Then what we need to do is we need to use our inferential statistics to say, okay, is that true for our bigger population again? Okay, and that's what inferential statistics are for. So again, we've got p-value and statistical significance. So p-value is basically the probability that the difference between our groups, right, is due to chance. Okay, now this sounds really complicated, but basically the idea is how likely is it that our findings are because of chance, that it just happened randomly that all of our people love pizza, right? Or is it because, that's part of that larger group? It's because it's applicable. Okay? Now, one thing that's important is you can never have a p-value of 0, right? And the reason for that is that we can never be 100% sure that there isn't due to chance. It's impossible. Okay? But the lower the p-value is, the better, right? The lower the p-value is, the better. So what we use the p-value for is to decide if we have what is called statistical significance. Basically, statistical significance just means that your findings are significant mathematically and can be applied to our bigger group. Okay? So for psychology, our p-value, right, what we're looking for is a p-value of less than, right, 0.05 or 5%. Okay? If we find that value, that means that we have statistical significance and we can apply our research to that bigger population. Okay? Now, another way to say that is basically if we have this p-value, if we have statistical significance, it means that there's a 95% chance that the findings are not due to chance. Okay? Because chance is something that affects all studies always, right? We don't know why someone gets better from being sick. We don't know why people choose to do this, not that. We don't know why some people recover from things and other people don't, right? There's always just random chance involved. So what we want to do is get our information to a point where we can be 95% sure, at least 95% sure that it's something new, right? At least 95% sure that this is the thing, our independent variable is the thing that caused this to happen, right? Or whatever else we're kind of doing. For some other fields like physics, I think they use a different number. I think they have a smaller number for statistical significance, but for psychology, it's 0.05 or 5%. Okay? All right. So again, please do a quick summary here to finish up. Again, no more than about 4 sentences.